Good day, my dear students. Welcome again to our lesson for today. Our next lesson is about factoring using difference of two squares. But again, before anything else, I want you to prepare yourselves. Get your notebook and your pen to take notes of the important details. Feel free to replay this video if there are things you do not understand. Are you ready? Let's recall. What is a perfect square? These are numbers or expressions that can be expressed to the power of 2. Examples. Number 1. 25 is considered as a perfect square. Why? Because 25 can be expressed to the power of 2 by multiplying 5 times 5. We can rewrite this one as 5 raised to 2. Therefore, 25 is a perfect square. Number 2, 16x squared is also a perfect square because we can multiply 4x times 4x. We can rewrite this one as the quantity of 4x raised to 2, which is equal to 16x squared, a perfect square. Number 3 example, 49y raised to 4. This is a perfect square also. Why? Because you can multiply 7y raised to 2 times 7y raised to 2, and also it can be written as the quantity of 7y squared raised to 2, which will give us 49y raised to 4, a perfect square. Let's try this. Determine if the given expression is a perfect square. Number 1, 4. 2, 10x squared. 3, 81b raised to 6. 4, y raised to 9. And 5, 169a squared b squared. Which items are perfect squares? And which items are not perfect squares? Let's check your answers. For number 1, 4. What are its factors? That's right, 2 times 2, which can be written as 2 squared, an expression to the power of 2. Therefore, 4 is a perfect square. Number 2, 10x squared. How are we going to factor this out? So what are the factors of the numerical coefficient 10? Correct. You can use 5x times 2x. Can we write it down as in the expression of the power of 2? No. So this item in number 2 is not a perfect square. Number 3, 81b raised to 6. What are the factors of 81? Correct. We can use 9. And in the variable, you can use b cubed times 9b cubed. So we can rewrite this expression in the form of quantity 9b cubed raised to 2. Then we can say in the item number 3, this is a perfect square. Number 4, y raised to 9. What are the factors of the variable y raised to 9? You can use y raised to 5 times y raised to 4. Can we express these expressions in the power of 2? No. So this item in number 4 is not a perfect square. In item number 5, 169 a squared b squared. What are the factors of 169? You can use calculator if you find the numbers difficult to compute. So we can use the numbers 13 and in the variable a, b. Multiply it by another 13ab. Can we express these expressions in the power of 2? That's right. We can express or rewrite this one as 13ab raised to 2. So this is a perfect square. Good job! Let's recall another concept that we can use in this lesson. That is the special product, sum and difference of two terms. So this concept is the product of a plus b and a minus b is equal to the difference of two squares, which is written as a squared minus b squared. Example, we have x plus 2 quantity x minus 2. If we are going to multiply this one, we can have x times x equals x squared. X times 2 is equal to, copy the sign, and then 2x. 2 times x is equal to, copy the sign, plus, and then 2x. 2 times 2 is equal to, the sign is minus 4. If we are going to simplify, you add similar terms. So the similar terms here are the following: negative 2x and another 2x. So negative 2x plus 2x is equal to 0. So we do not need to write it down in the simplest form. So our final answer must be x squared, and then cancel out, copy the operation minus, and then bring down 4. As you can see, the product of the sum and the difference of two terms is equal to the difference of two squares. This is a perfect square, and this is another perfect square. So we have recalled perfect squares, and the concept of the sum and difference of two terms. Now, we are ready with our lesson. Our lesson is about factoring difference of two squares. We have a squared minus b squared, the difference of two squares, and their factors are a plus b times a minus b. Simply the sum and the difference of the two terms. Example number 1. Write x squared minus 16 in completely factored form. Solution. Step 1. Express the first and the second terms in exponential form with the power of 2. X squared can be written as x times x, or the quantity x raised to 2. On the other hand, 16 can also be written as 4 times 4, or the quantity of 4 raised to 2. Step 2. Subtract the two terms in exponential form following the pattern a squared minus b squared. So first, copy the quantity x raised to 2 minus the quantity 4 raised to 2. Step 3. Factor completely following the pattern. A squared minus b squared is equal to a plus b times a minus b. So to factor out, x plus 4 times x minus 4. Conclusion. Hence, the complete factored form is x squared minus 16 is equal to x plus 4 times x minus 4. Example number 2. Write 4a squared minus 9b squared in completely factored form. Step 1. Express the first and the second terms in exponential form with the power of 2. The first term, 4a squared, can be written as 2a times 2a, or the quantity of 2a raised to 2. On the other hand, the second term, 9b squared, can be written as 3b times 3b, which is equal to the quantity of 3b raised to 2. Then we can assure that the two terms are perfect squares. Step 2. Subtract the two terms in exponential form following the pattern a squared minus b squared. So copy the quantity of 2a raised to 2 minus the quantity of 3b raised to 2. Step 3. Factor completely following the pattern a squared minus b squared is equal to a plus b times a minus b. So the factors are 2a in the first term plus 3b for the second term, and then 2a for the first term minus 3b for the second term. Hence, the complete factored form of 4a squared minus 9b squared is equal to 2a plus 3b times 2a minus 3b. Example number 3. Write the expression m squared n raised to 4 minus 25 in completely factored form. Again, step 1, express the first and the second terms in exponential form. The first term, m squared n raised to 4, can be expressed as m n squared times m n squared, which can be written as the quantity of m n squared raised to 2. The second term, which is 25, can also be written as 5 times 5, which can be expressed with the power of 2 as the quantity of 5 raised to 2. Then, we are sure that the two terms are perfect squares. Step 2. Subtract the two terms in exponential form, following the pattern a squared minus b squared. M n squared raised to 2 minus the quantity of 5 raised to 2. Step 3. Factor completely following the pattern a squared minus b squared is equal to a plus b times a minus b. So, the factors of the expression are m n squared plus 5 m n squared minus 5. Hence, the complete factored form of m squared n raised to 4 minus 25 is equal to m n squared plus 5 times m n squared minus 5. Example number 4. Write the expression y raised to 4 minus 16 in completely factored form. Step 1. The term y raised to 4 can be written as y squared times y squared, or the quantity of y squared raised to 2. Also, the second term, which is 16, can be written as 4 times 4, which is also equal to the quantity of 4 raised to 2. In the step 2, we are going to write down the exponential form following the pattern a squared minus b squared. So copy the quantity y squared raised to 2 minus the quantity of 4 raised to 2. Then, the step 3, we are going to find the factors. Using the pattern a squared minus b squared is equal to a plus b times a minus b. So what do you think are the final factors of the expression? Let's check. So the factors are y squared for the first term plus 4 for the second term times y squared again for the first term minus 4 for the second term. But we can also factor out this expression y squared minus 4 because y squared is a perfect square And 4 is also a perfect square. So let's check what are their factors. So y times y and 2 times 2. So we can rewrite the factors of y squared minus 4 as y plus 2 times y minus 2. However, y squared plus 4 cannot be factored out because it is not a difference, but it is a sum. Okay? So all we need to do is to bring this down. So copy y squared plus 4. Hence, the complete factored form of y raised to 4 minus 16 is equal to y squared plus 4 times y plus 2 times y minus 2. Example number 5. Write the expression 3a squared minus 27 in completely factored form. Step 1. Express the first and the second terms in exponential form with the power of 2. But as you can see, is 3 a perfect square? Is 27 a perfect square? No. But kindly observe that we can use the greatest common factor of 3 and 27, which is 3. So we are going to factor out 3. And then the remaining factor is a squared minus 9. So our new expression that we need to factor is 3 times the quantity a squared minus 9. Now, we can say that a squared and 9 are perfect squares. So we can proceed with our solution. So a squared can be written as a times a, or in the exponential form, the quantity of a raised to 2. On the other hand, 9 can be written as 3 times 3 in the exponential form, that is, the quantity of 3 raised to 2. So we can proceed with our step 2 using the pattern a squared minus b squared. So our first term is equal to the quantity of a raised to 2 minus our second term, the quantity of 3 raised to 2. Step 3, we are going to factor out completely following the pattern. But first, you need to copy our greatest common monomial factor, 3, and then identify the factors. Our first factor is a plus 3, and our second factor is a minus 3. Hence, the complete factored form is 3a squared minus 27 is equal to 3 times the quantity a plus 3 times the quantity a minus 3. What did you learn today? Today, we have learned factoring difference of two squares. How do we factor difference of two squares? So in general form, if the given difference of two squares are a squared minus b squared, the factors are the following: a plus b and a minus b. It's your turn.